Окей. Спасибо за приглашение, Алексей, Федор. Спасибо за присутствие всем студентам и студенткам. Большое удовольствие для меня провести здесь в Ярославле эту неделю. Я буду говорить об очень классической теме зета-функций. Все началось 2 века назад с Eulerом Dirichlet, Riemann et Adamar de la Vallée-Poussin. И сегодня зета-функции можно найти везде в арифметике и в алгебраической геометрии. Конечно, это курс только введение. Если вы не понимаете что-то или я сделал ошибку на доске, пожалуйста, говорите, спрашивайте. И извините, но говорить целый час по-русски мне еще слишком трудно и, может быть, слишком утомительно для ваших ушей, поэтому я продолжу по-английски. So the topic of my course is a very classical topic. I will start actually with very classical things, and then I will move during the week to more modern mathematics involving cohomology and this kind of stuff. But let me start by the very beginning is of course the Riemann zeta function, which should be called Euler-Riemann zeta function, which is, first defined as a series. And, the very first thing that you show, it's actually, you can write it also as what is called an Euler product. So this is the product of all primes. So this is really just an analytic statement of the uniqueness of factorization of numbers. If you expand this to sum of p minus ms, and you take the product of all p, then if you expand again the product, at least formally, you obtain the sum over all the products with all possible powers to the minus s. And at least formally, it's obvious that it's equal to that if you know the uniqueness of factorization of numbers. And of course, I won't give the details, but you can make this rigorous when the real part of S is strictly greater than 1. So this is basically the Z zeta function. That's difficult to translate in Russian, but Z means it's really the main zeta function. And it was used essentially by Riemann to, not entirely prove because his paper contained a gap, but it was mainly used to prove the so-called prime number theorem. So the way to prove it was really invented by Riemann, but the proof is those two people who proved it sort of 30 years later. So it states that the number, so that's the number of primes less than x, that it is, well, asymptotically like x over log x. It's quite a deep theorem. It's not trivial at all. And it was, in some sense, the first major achievement of analytic number theory. Curiously, previously to that, there was the paper by Dirichlet. So what Dirichlet proved is the following thing. The first thing is that if you take two numbers which are co-prime, then there is one or infinitely many primes congruent to A modulo n. So there exists a prime P congruent to A modulo n. This is again a deep result. I mean, for small values of n, for n equals 3, 4, you can prove this elementarily. But already for, let's say, to prove that there's infinitely many primes congruent to 3 modulo 8, you need some deep theory. It's not easy at all. So to prove that there's one or infinitely many, it's the same in this case if you prove it for all moduli, because once you have one, if you repeat the argument and you find infinitely many. So in both those statements, of course, there is no zeta function, but each time it is proven with some zeta function. So perhaps I will introduce right away what are the zeta or L functions that are used by Dirichlet. They are the so-called Dirichlet L functions. So it's a variation, actually, of the zeta function, even if they were considered before by Dirichlet. What you do is you consider, well, I will consider what is called a Dirichlet character. So usually a character is a homomorphism from a group to C star. In this case, I take the finite ring Z over NZ, the invertible elements, and chi will be a homomorphism to C star. And I extend it to all values of integers. So if I will define chi of m for m in Z, well, you define it as chi of m modulo n if the two elements are co-prime. So if this lies in the invertible elements, and I define it just as the... So I use the same, I should actually use a different letter or some tilde, but I dropped the tilde. There will be no confusion, and 0 otherwise. Then the variation of the zeta function considered is the following function that is classically denoted like this. It is the sum for n equals 1 to infinity of, well, you add a coefficient chi n minus s. Then the analogy with the Euler product is rather easy to prove, basically because this function chi remains multiplicative. It's obviously by definition multiplicative here. I mean, chi of mn is chi of n, chi of m, but it remains true even with that definition. So it's quite easy, essentially by the same proof, to show that you have this formula. So you have an Euler product. Again, this formula is valid for real part of S strictly greater than 1. And it is using those functions that Dirichlet proved this theorem. So I will now explain a bit more. So this will be a general phenomenon. Any series like this will always be convergent on a half plane. I will prove that in a moment. Of course, not every series like this has an Euler product as a product of primes. That's a special properties. Now, in general, the values of the function in the half plane of convergence, of absolute convergence, is useless. You cannot use it. You cannot deduce anything from it. So you have to analytically continue the function, and it's the value beyond the line of convergence that are really useful. So perhaps I will say first concerning the zeta function. So again, it's due to Riemann. Is that you can continue analytically the zeta function. So zeta of S can be analytically continued. Well, the whole complex plane, except so there is one pole that you cannot avoid, except at S equals 1, where there is a pole with residue 1. So it's simple. A simple pole with residue S equals 1. And further, there is a symmetry in the zeta function. So that's the first deep theorem that Riemann proved. So perhaps I should recall, if you don't have this in mind, that a holomorphic function is entirely determined by a neighborhood. I mean, there's only one. If two holomorphic functions coincide on a small disk, they coincide everywhere where they're defined. So analytic continuation, if it exists, is unique. And therefore, well, it's nice that it's unique, but it shows that it's difficult to prove. It's in general very difficult to extend analytically a function, and of course not always possible. So this is already quite some theorem. But further, there is a symmetry, which is a so-called functional equation. Which can be stated like this. Well, first you need to introduce the Euler's gamma function. So actually I should mention, I'll mention Euler once I have written the statement. So this is Euler gamma function. So it is the integral from 0 to infinity of exponential minus t, ts minus 1 dt. So it's an exercise for first or second year student to show that this is convergent for real part of S positive. But it is also an exercise, it's by integration by part to show that S gamma of S is equal to gamma of S plus 1. So once you have this, you can easily extend the gamma function to the whole complex plane just by translation, and repeating the arguments. You get poles. So this gives an extension to C minus. You have to take away the negative numbers because each time you divide by S and by S plus 1. So at S equals minus 1, you get a pole, etc., etc. Now, if you define the function psi of S, the notation is standard. I don't dare to change it, even if on the blackboard zeta and psi look quite the same. But so you multiply pi S over 2 gamma of S over 2 zeta. Then this has analytic continuation with the pole at actually S equals 0 and S equals 1. And the fundamental thing is that there is a symmetry this has the following. So I will give a bit later the proof of that because it's such an important feature of the zeta function. But what I want to underline right away is the following picture. That's the complex plane. So in some sense, the zeta function is defined by a nice series or Euler product in this region. So there, it's rather easy to see the property of the zeta function. In particular, for example, this formula shows that the zeta function does not vanish in this half plane because it's a product of non-zero terms, so it cannot vanish. This symmetry makes it that you also know very well the zeta function here, because essentially it's the same values. You just have to multiply by the gamma function, which is a much simpler function than the zeta function. And so you're only left with what is called the critical strip, where, as we will see, we have formulas for the zeta function, but the formulas are not as useful. You don't see as well what happens there. And in particular, it's a total mystery where the function vanishes. What you can say from the functional equation is the following symmetry, is that, well, there are two things. If you have a zero, well, this is very unlikely to happen, but suppose you had a zero here, then, well, it's quite easy to see that if you have a zero, the conjugate is also a zero. So if you have a zero here, you have one here. And because of this condition, you also have a zero here and here. So the zeros are symmetric with respect to this axis. And there is a statement in Riemann's paper, which still remains unproven today, so more than a century and a half later, is the Riemann hypothesis. Well, it states that if psi of S is zero, then the real part of S is 1/2. So that I should perhaps write. This is, I will write Ri, so that's not proven, it's a question. Why it is such an important question is not clear right away. And obviously at the time, it was not taken as one of the big problems. I have a proof of that. There is a note in Compte Rendu de l'Académie des Sciences of Stilges, not a rubbish mathematician, where he announces a proof of that. And this was published by the French Academy. And of course, the proof never appeared. The proof was supposed to appear later, but it never appeared, and obviously Stilges found an error and but never advertised the error. Nevertheless, what is known is a much weaker statement that states the following. So, in his paper, Riemann sort of proved the functional equation and said, well, that looks true. Well, he said it in German, but I don't speak very well German, so I won't repeat it in German. That this looks true, and in some sense he uses it to prove the prime number theorem. So the proof was incomplete. What Adamar and de la Vallée-Poussin proved is the following: is just that the function does not vanish on the line. It's of course a much weaker statement, so I will state it like this. So for all t, this is non-zero. And so I'll give the proof of that because it's such an important statement. And it's a very tricky proof. You wonder, how can you invent such a proof? And it doesn't give you any clue of why that should be true. A little more is known. Actually, you can extend to some regions like this. I mean, you can draw regions like this where you know that there is no zeros, but all the regions know they tend to this line. But we are very far from the Riemann hypothesis in that sense. There are many results around the Riemann hypothesis. I won't speak too much about that because, well, I don't want to focus too much on the analytic part. I want to go later to the algebraic part. But I'll give a proof of that. And this is just enough to prove the prime number theorem. And it is absolutely essential. I mean, there's no proof with using complex variables which do not use these results. The story for the Dirichlet L function is in some sense similar. It's probably it's in fact a little easier. Is that the series the sum phi n of n minus s actually is absolutely convergent for real part of S greater than 1, but it's not difficult to see that it's convergent for real part of S positive. It's convergent for real part of S positive. The reason, maybe I will write it. Well, I'll give the proof later. I'll give proof of this and this later. For the moment, I just give the statement to give a picture. And the fundamental point to prove the arithmetic progression theorem, you need to prove that actually that L of 1 pi is non-zero. This is the main statement. Just like to prove the prime number theorem, this is what you have to prove the arithmetic progression theorem. I will explain the argument again later. What makes this slightly easier is that, well, you have the same picture, absolute convergence. The L function also satisfies a functional equation, and so you have a symmetric, but it's a bit easier because the series converges until 0. So actually the point at S equals 1 is a point where the series converges. There's an amusing thing is that if you knew that or I've erased the Euler product, if you knew that the Euler product would converge at S equals 1, you would deduce right away that this function is not 0 there. Now it is true that the Euler product converges at S equals 1, but you need to use that, sorry, this is non-zero. You need to use that to prove it. So you cannot use it directly. So the philosophy is that it is important to study the values of zeta functions beyond the half plane of convergence and to know where it vanishes or not, at least for asymptotic results like this. Now, well, perhaps I won't write the functional equation. The functional equation for this function is very much it's very similar. I mean, you have to write, you define lambda chi s. So there is the number n. You remember that this is the n from the character. There is a little twist that I will explain later. So you have to put n minus n to the power s pi minus s over 2. There's a gamma of s plus delta over 2. and L of S chi. So I can always define this function. It does not always have the good properties. I have to say what is delta. So delta is 0 if chi of minus 1 is 1, and 1 if chi of minus 1 is minus 1. Of course, chi of minus 1 square is equal to 1, so the chi of minus 1 can only be 1 or minus 1. There is, well, still, the definition is still correct, but to have a functional equation, you need one more hypothesis. So you have to assume that chi is primitive. So what does primitive mean for a character? Well, there is a small perturbation that you can do with characters. Is the following: suppose that your character factorizes like this. So the first one, say for m dividing n. Well, you have an obvious map for m dividing n. Well, to a class modulo n, you associate with the same class modulo m. That's a homomorphism. And suppose that you started with the chi 1. Suppose your chi is like this. Then you say that the character is not primitive, because actually it comes from a smaller modulus. Now there is a little complication in the following sense. If you compare the value of chi of m and chi 1 of m in that situation, so what I mean is that m divides n, and m is different from n. So you have equality. So if, well, m is equal to 1 by construction, you also have equality if, well, m is strictly greater than 1, because then they will both be 0. But they are not equal if mn is not equal to 1 and m is equal to 1. So there are very few values that are different, but they are not exactly the same Dirichlet character. So if you look at the L function that they define, they are almost equal, but not quite. So perhaps I should write this here. So if I'm in this situation, well, I claim that the two functions, they are almost equal, but not completely equal. Actually, if you make the computation, you find the following formula. So this is a finite product. This is for p dividing n and p not dividing m. So there's only a finite number of factors, but still that makes a small perturbation. So it's not very complicated to compare the two. And if I want to formulate the functional equation, so the functional equation will be that this lambda of S chi is equal to, well, a number W chi L S, L1 minus S, and it's not chi, it's chi conjugate. So the functional equation will be like that, but I have to assume that the character is primitive. So W chi is just some number. It's not plus or minus 1, it's a complex number of modulus 1. So the point that I want to make is that this formula cannot be true both for chi1 and for chi, because it would imply that this function has a nice functional equation, and that's definitely not true. That's easy to see. So that is true only for chi primitive. So that I will not give the proof because it's very similar to the proof of the Riemann for the Riemann function, and it's just the same ideas with more notations and complications. So we have again the same picture, and you can again make the Riemann hypothesis, which we can't prove, but it's perfectly reasonable, which means that inside the critical strip, the zeros are on the axis of symmetry. And this again would have important consequences. But for the arithmetic progression theorem, the only thing you need to know is this. Okay, so that's for the really the old classical zeta function. Let me explain perhaps what is, why those statement comes into the proof of the prime number theorem and the arithmetic progression theorem, and then I'll give the proof of the functional equation, the Riemann zeta function. Well, first I have written for the moment so only the series and the Euler product for the zeta function, but it's relatively easy to write a formula for the logarithm of zeta of S. Of course, since it's a complex function, I need to make some choice, and it is the principal branch of the logarithm. I mean, zeta is real for S real greater than 1, so I choose the log which is real. Well, if you take the Euler product and you take the log of the product, you end up with a formula like this: the sum over the primes and sum over m greater than 1 of p minus ms over m. That's quite easy. That's almost formal. And you also have a formula for the logarithmic derivative, which is very useful. So I will put minus, the formula is neater. And here you get the formula, well, the sum over p, the sum over m of log p minus m. So that it is classical to rewrite this as the sum over all n of lambda n minus s, where lambda n is a so-called Mangold function, which is log p if n is the power of p, the power of a prime, and 0 otherwise. Okay. And you have, well, almost the same formulas with the Dirichlet function, which I don't write, but I will use that. They are entirely similar and derived in the same way. Maybe I'll keep those two here. So perhaps I will start by reproving Euclid's theorem. There's infinitely many primes. Before showing there's infinitely many primes congruent to A mod n. Well, it's just enough to look at this series, for example. If there were only finitely many primes, okay, well, this function would be entire. But it's not, because it has a pole at s equals 1. Okay, so that's an analytic proof of there's infinitely many primes. Now, the proof that there's infinitely many primes congruent to A modulo n is a bit in the same spirit. So what you do is, well, I will start with an elementary formula, which is purely algebraic, that if you take the sum over all characters, modulo n, of chi x, that's a purely algebra exercise, that this is 1 if x is congruent to A modulo n, and 0 otherwise. It's a so-called orthogonality of characters. Here, the sum, I take the sum is for, well, let me introduce G, this group, and the dual is just the homomorphism from G to C star, and chi is in, you take all the characters. So it's really, it's a little exercise in algebra, which is not difficult, and by the way, very useful and interesting. So with that, I mean, if you take any function, I will choose, let's say I will choose the sum of P minus S over P congruent to R modulo n. And actually, I want to show that this is not an entire function, that this function diverges somewhere. So that will prove that there's infinitely many primes congruent to A modulo n. So I can choose, and one can choose other functions here, that it's a general mechanism. So if I do that, well, using this, I can rewrite this as, well, 1 over phi n, the sum over chi of chi A, and then the sum over chi p, p minus s, and that one is over all p. So I can separate this in two parts. Of course, there is, I will call, there is always the so-called trivial character, which just gives the value 1 to all the elements. So I have to separate this one, because this one gives me something like this, 1 over phi n, and just the sum over p minus s over p. So that function, either through Euclid's argument or whatever, I already know that this has divergence. It's not an entire function. It goes to infinity somewhere. Now I write all the other terms. The other terms you can write as the sum of chi different from chi naught. I will keep the phi n. Well, chi a, and then you get the sum of chi p, p minus s over p. Now, I look at this function, the sum of a 1 of a p minus s, that really looks like this. So what I mean is if I take the log of L of S chi, well, don't do the proof. It's really not difficult to see that this is the sum. So over p, the sum for m greater than 1 of chi m p s over m. That's really almost formal. So this you can rewrite as the sum. Well, I separate the sum for m equals 1, so chi p minus s, plus, well, the sum over all p, but for m greater than 2 of the same thing. Now, what do I see? So there is my function, the function I want to estimate. Well, this one is not too difficult because if there is a square, well, we've seen that the series was absolutely convergent for real part of s greater than 1. So actually, this one is absolutely convergent for real part of s strictly greater than 1/2. So this is so holomorphic for real part of s strictly greater than 1/2, and in particular, it's bounded near 1. So it's bounded near 1 because it's holomorphic there. It's bounded. So now I look at what happens when s goes to 1. So when s goes to 1, I know that this series diverges. Or I know. It's easy. I've given essentially the argument here. Zeta has a pole at s equals 1. So when s goes to 1, this series explodes. So I know this goes to infinity. Now I claim that, well, when s goes to 1, this is bounded. So this function is equal to a bounded function plus something that goes to, well, the value at s equals 1. So what I conclude is that if L of 1 chi is different from 0, then the sum of a chi p minus s is bounded near 1. So, but I need to know that, of course. If I don't know that, I can't conclude. But if I know that, then I conclude that this series is equal to a series that diverges when s goes to 1 plus a bounded function. Therefore, this one goes to infinity also, and that means there's infinitely many primes. I'm going to a modulo n, sorry. So that's why it's crucial to have this, and also, in some sense, it tells you that the primes are equidistributed in the classes modulo n, because, well, there's phi over n classes modulo n that are co-prime with n. And at least for this function, it tells you that there's exactly the right proportion up to a bounded term. So it tells you in a quite precise way that the primes are equidistributed in classes, in residue classes, modulo any integer. So, well, that proof gives the feeling of why such statements like non-vanishing of L functions, special values of L functions are important. Well, it's harder to prove the prime number theorem. So, well, that proof is essentially complete, except I have not yet proven this. This is by a different argument. So the prime number theorem I won't prove entirely, but I will give an idea where the non-vanishing statement comes into. Actually, what I'll do is I'll give two samples of covariance theorems. The first one is due to Ikehara. And, well, it says the following, that if you have, say, a function, I call it Z, not necessarily zeta, but it will look like a zeta function, that's defined as a series like that, but with a n positive. And we suppose that it is convergent for real part of S strictly greater than 1. So until so far, this is not a very, these hypotheses are not very difficult. I mean, it's true for the zeta function, it's true for the minus the logarithmic derivative. What I add now, and suppose further that the function z minus lambda of s minus 1, this one you can analytically continue along the line. So is holomorphic for real part of S at least 1. So this is really the nasty hypothesis, well, the hypothesis that's really non-trivial. The other ones are simple, this one is a bit complicated. Suppose you have that, then, well, if you take the summation of the coefficients, this will be equal to lambda x plus a little o of x. Well, I hope, is everyone familiar with the notation big O of x, a little o of x? Okay. Now, why is that called a Tauberian theorem? Well, it's a relatively easy exercise to see that if you have this conclusion, then the function z has a pole with residue lambda at s equals 1. That's relatively easy to see. That's an easy exercise. Now, the converse is not true in general. So the content of Hikehara's theorem is that if you add those hypotheses, then it becomes true. Now, let us see that this theorem applies to the logarithmic derivative of the zeta function. So perhaps I will still keep that here. So if you look at the function, well, minus zeta of s, well, we've seen that I have written it like this, the sum for n equals 1 to infinity of what I call lambda n. Well, the lambda n's are clearly positive. They were either logarithm of a prime number or zero. They're positive. It's certainly convergent for real part of S greater than 1. Everything we've done is convergent in this region. Now, do we have something like this? I mean, I want to show that there is a lambda. So what I claim is that so this function has a pole of order 1 at S equals 1 with residue 1. Well, this is just holomorphic function theory. If a function has a zero of order R, then the logarithmic derivative has a pole of order 1 with residue R. So here the zeta function has a pole of order -1. So if you take minus the logarithm derivative, it has a residue like this. Now, is it holomorphic along the line real part of S equals 1? Well, yes, because of that. Otherwise, it would be false. So it is holomorphic for real part of S equals 1. So of course, outside of 1, because of that's the result of Adama de la Vallée-Poussin. That because you know that, the function is holomorphic and non-zero, therefore the logarithmic derivative is holomorphic. But you really need to know that. Then, if you know that, the conclusion is that the sum of lambda n for n less than x, well, in that case, what it says is that this is equivalent to x. And it is elementary to show that this is equivalent to the prime number theorem. This is perhaps I'll do these things later, but let's say I will leave it as an exercise. Упражнение. Another version, which is actually easier than the Ikehara theorem, which is interesting, I'll give another Tauberian theorem, is the following. So this is due to... Actually, the version I'm going to give is due to Zagier, but this is just a modification of a theorem of Newman. So I start with a function, I will assume that it's locally integrable, that it's bounded. Well, I don't to put two general hypotheses, so that's enough. Then I consider the Laplace transform. So it is not too difficult to show that this is always convergent and holomorphic for real part of S, strictly positive. Well, it's not difficult because the function is bounded and this is very fast decreasing, so it's not surprising, it's not difficult. So I add the hypothesis, suppose it extends to real part of S equals 0. I will put positive. So that's a hypothesis that looks a little bit like this one. I mean, you assume that you can push just a little further the analyticity. Then the conclusion is that, well, f of 0 is well defined. If you can extend the function, there is a value. Well, what it says is that this is equal to the integral. And, of course, the statement contains that this is convergent. In some sense, the most important statement is that this integral is convergent, which is not obvious at all. And further, you have the value. So this theorem is actually a lot easier than Ikehara's theorem. I won't give the proof either, but it would be easier. So how do we use it for the theta function? Well, I will introduce one more notation. Well, this function, it's so useful. It's usually denoted psi of x. These are Chebyshev notation. There is another function that was introduced by Chebyshev, which is a small variant. It's the sum of the log p. So what you do is you apply this to the following function. That's the integral of theta of t minus t over t s plus 2 t t. So the outcome, I mean, we're going to show that this integral is convergent, so that you can apply the theorem here, and therefore we're going to conclude that this integral is convergent. Now, it is, again, an elementary exercise to show that this implies the prime number theorem. What do you do? Well, first, you prove that theta of x is equivalent to x. And then you're back to the previous exercise, because the difference between psi of x and theta of x is very small. That's, again, is easy. So how do you deduce this? I'll just give really quickly the argument. Suppose that, let's say that, you look at the limit sup of theta of x over x. You suppose that it's at least 1 plus epsilon. I mean, it's strictly greater than 1. Suppose that. Well, I claim then that it's easy to show that this integral is divergent. Because if this is essentially on large chunks greater than 1 plus epsilon t, this integral on large part will be greater than some constant times t over t squared. So it will be greater than the integral of dt over t. But that's divergent. So you show that the limit sup is smaller than 1 with that argument. And with the same argument, you show that the limit inf is at least 1. Therefore, the limit is 1. So that's, I mean, let's say it's tricky, but it's not difficult. But I need to explain why the hypothesis of the Newman's theorem apply to this. So that's a small that's a small change of variables. So let us make the change of variable I will call t equals exponential u. So I hope you remember I haven't done change of variable for a long time, but so if you write this, you will get the integral, sorry, here. So 1. So you get the integral from 0 to infinity of theta of exponential u minus exponential u. Well, I will write this for f of s over well, the exponential of u s plus 2, and dt is exponential u du. Okay, that looks like a Laplace transform. So you get the integral from 0 to infinity. So I want to keep here only exponential minus us du. So I get rid of this. I have two u's, one that goes away, and so I have to divide this one. So I get theta of exponential u exponential minus u minus 1. Okay, so that's my function h of u. So what do I need for that? Well, it's certainly locally integrable because, well, the function theta is just a staircase function, and exponential is continuous, so I mean, there's no problem of locally integrable. It's bound. Well, you need to know that theta of x is bounded by some constant time x. So that's quite elementary. That's again in Chebyshev. Well, for example, by the binomial theorem, you have this inequality. Therefore, if this is divisible by all the primes between n and 2n, so you get that theta of 2n minus theta of n is smaller than n times log 4. Okay. I mean, this is an integer, and if I take a prime that's smaller than 2n, it divides 2n factorial, and it cannot divide n factorial. Therefore, it divides as that integer. So when I take the log, it appears in the sum. And once you have that, it's elementary manipulation to deduce that, for example. That's what I mean by elementary argument. So, it satisfies those functions. Now, you need to know if this extends to real parts of S equals 0. So that's where the zeta function comes in. If you write exactly what is this function, it's actually closely related to the zeta function. I will write this here. So the idea is to, well, I will write it like this. I will first write, I can't, I can't cut the two in two because then there would be diversion here, but I can do that for s greater than 0. So I'll do that on this level. So the sum the sum of 1. Otherwise there would be a singularity at 0. The sum over 1 at infinity f of s, well, I write as the sum from n equals 1 to infinity of the integral from n to n plus 1 of theta t minus t over t s plus 2 dt. And then that's nice because then the function theta is constant. So this is the sum for n equals 1 to infinity of, well, theta of n, and then the integral from n to n plus 1 of t minus s minus 2, and minus the integral between n and n plus 1 of t minus s minus 1 dt. So that's, well, that's t minus s minus 1 over minus s minus 1 between n plus 1 and n. So that gives us the sum of theta n, well, over s plus 1, and here I have n to the minus s minus 1 minus n plus 1 minus s minus 1. And, well, the other, I forget, I leave it I leave it just the same. Now, on this, I can make an Abel transformation. I will get, perhaps I'll write on this one. So I will get something like the sum 1 over s plus 1, the sum, well, over n minus s minus 1, and what do I get? I get theta of n minus theta n minus 1. So I forgot about the rest, which doesn't change, which gives a simple term. Well, this is quite simple. I mean, theta n is the sum of log p for p less than n. So this is equal to, well, either it's equal to log p if n is equal to p, or it's equal to 0. Okay. So you get a function like this, sum over p minus s minus 1, the sum over p. Now, we've already looked at this function. This is essentially the logarithmic derivative. Sorry, I've lost a log p somewhere. No. Yeah, I lost a log p. Yeah, that's it. It's here. Okay. So it's essentially the logarithmic. I mean, when I wrote minus zeta of s plus zeta of s, it's the sum of log p minus s plus, well, something that's holomorphic for real part of S greater than 1/2. But I don't write. I mean, what you would get with the m greater than 2. So essentially, this function is exactly holomorphic where this one is. And therefore, well, you have to analyze the two cases. The case, what happens at S equals 0 and S equals IT for t different from 0. So the case S equals 0 is just analyzing the pole, and in that case, you mustn't forget this term, because it's exactly this term that cancels the pole. But the most important point is, at this point, well, you get actually the function, you know that you need to use that zeta of 1 plus IT is different from 0. So this function is holomorphic at this point, and therefore this one, which is just translated by 1, is holomorphic at this point. And so you can use Newman's theorem and conclude. So in both proofs, in quite different ways, essentially the main tool is this non-vanishing of the zeta function. Okay. So that's mainly the analytic part that I wanted to explain. So this, as I said, a very classical result. Except the Ikehara and Newman's theorem are more recent, but essentially the classical proof of the prime number theorem uses more complicated analytic argument, but essentially the same. So those functions, well, they are obviously, I mean, they were constructed to study the distribution of prime numbers. So there is, I want to conclude the last 15 minutes with sort of broadening the scope of use of zeta function. So So the first one that I explained, the classical, is the, well, distribution of primes. And certainly it remains a very important activity. So the two main theorems are the arithmetic progression theorem and the prime number theorem, but there's many continuations. Now, there's lots of other uses that have appeared progressively through different. The other thing is to use special values of zeta function. Of course, you need then you need many zeta functions. For the moment, we have the Riemann zeta function, but there's only one. And we have, well, the Dirichlet L function, then there you have infinitely many. So you can already start to study things in terms of the conductor, etc. But if you introduce with more zeta functions, then you can study special values that are interesting and deduce things from these special values. That will be actually the main focus of my lecture. The idea is that sort of special values gives deep arithmetic geometric results. I'll give a first example of something that can be proven along this line. And then I'll give a list of things I will talk in the next lectures. Well, for example, well, if you consider a number field finite extension of Q. Well, you have the so-called ring of integer. And for this reason, those are very much studied. And one of the main problems is the so-called the study of the class number. So I will define HK. This is, well, I'll give a, for those who know what the Picard group is, it's just the cardinality of the Picard group. There's a much more elementary definition. It's the number, you take the ideals modulo the principal ideals. You can multiply two ideals, that's clear. So you will say that two ideals give the same class. If multiplying by principal ideals, you can get from one to the other. So it's a classical theorem that this is a finite number. And, well, from this definition, it's obvious that the ring is principal if and only if this number is 1. So here's a statement, for example. For k equals q of, well, an imaginary quadratic field, the class number goes to infinity with d. Same thing if I take the cyclotomic field, q of, well, I over d. Then, of course, as d goes to infinity, the class number goes to infinity. There's no algebraic proof of that. All the known proof uses more or less zeta function, and I mean, there's no algebraic construction proving this. So this is, but the use of zeta function, that will be the main topic of the next lectures, is not restricted to just arithmetic. It is also extremely useful in algebraic geometry. So I want to propose the one definition at least of the so-called Hasse-Weil zeta function that will give us also Dedekind zeta function and a lot of classical examples. And I want to explain that the definition is just copied from the Riemann's definition. You just have to think that, well, if you think of the ring Z, well, all you have to know is that the prime ideals, the spectrum is, well, the zero ideal, and the set of ideals generated by a prime number. So you have to interpret P in that case as the cardinality of Z modulo Pz. Then I will write the zeta function that I will call the zeta function associated with the ring Z. That's just the product of a prime, well, of a, I will write maximal ideals. That's shorter to write than say it's prime and non-zero in that case, of, well, 1 minus the cardinality of Z over M to the power So that's just, of course, a rewriting of the Riemann zeta function. Now, why did I do that? Is that now if I take, instead of Z, let's say I take a ring, sorry, that's A in French. A ring is anneau in French, so I always write A for a ring. So what property of the ring do I want? I want that the quotient by maximal ideals should all be finite. So then it's clear what is the condition. I want it to be a finite type over Z. Then it will be true. Then I can define the zeta function as the product. Well, I take this exactly this formula: 1 minus the cardinality of A over M minus S minus 1 for M maximal ideal. Why is this a very interesting object to consider? We'll see later, but it's clearly, I mean, it's a simple extension of the Riemann zeta function. And once you've formulated it like this, and if you have the general language of schemes, it's easy to extend it to schemes. So if I take X, a scheme, a finite type of Z, I can take exactly the same definition, except what I take closed points. So I will define Z, X, S as the product. So I write X. So this means the set of closed points. Of 1 minus, well, there is a notion of residual field that's usually denoted kappa of X minus 1. Actually, not really that much more general than this. If you think the fact that you can always cover a scheme with finitely many spectrum of rings like this, and actually you're just taking pieces of it, except that you don't repeat twice the ideals that would belong to the two, and you get this definition. It automatically has an Euler product because, well, if you have a scheme of a spec Z, then, well, you have closed points here, which are just the primes, and so above you have the fiber, which is XP, which is, if you want, the reduction modulo P of your scheme. And it's absolutely formal that this is equal to the product over all P of the zeta of XP of S, because it's just the union. Now, it turns out, so that I will show on, the next lecture is on Sunday, that this is closely related to the so-called veil zeta function, to the so-called veil zeta function of a finite field, of a variety of a finite field. This is essentially a variety of the field FP. And so, considering this, so we'll study first those functions in characteristic P, and then how they glue together to give a global zeta function. And I mean, there are many more conjectures and theorems on special values, but still, there are many results. So the most classical example is the Dedekind zeta function. So if you take zeta of, with this notation of the ring of integer of S, then that can also be written as 1 minus the norm of P minus S minus 1, where P is a prime ideal, non-zero, because for rings of dimension 1, to be maximal is the same as being non-zero and prime. And perhaps it's also time to write down the hypothesis that we expect from this from those functions. So the property that we expect. So many things in mathematics are called zeta function. I mean, Yurichenko will give a course that's called the height zeta function. So unfortunately, his height zeta function don't belong to this category. But still, in arithmetic, it's natural to call zeta functions things that will be, well, first, the function should be defined by some Dirichlet series. That's the first thing. So convergent in some half plane. It should have an Euler product. This means that this should be equal to the product of Zp of S, where Zp is something. So I want to write a polynomial in P minus S to the power minus 1. So it should be something like the product of 1 minus P minus S minus 1. J equals 1 to D. Further, to suppose this is essentially already guessing the either the Riemann hypothesis or the Lin-Grothendieck theorem. You suppose that all the alpha JP, well, they should be, the absolute value should be some power of P, and further they should all be bounded with equality almost for all, with equality for almost all. You should have a functional equation so when I write functional equation, I mean I include the analytic continuation. For the moment, this is defined only on the half plane. It should extend to the whole complex plane, maybe with some pole, but and satisfy a functional equation. The functional equation should be something like, some number, some gamma factor, times z of s, should have a symmetry. So here the symmetry is SW minus S for this W. And of course, you can add the Riemann hypothesis if you like, but the Riemann hypothesis is not proven for any zeta function in characteristic 0. It's only known in characteristic P, so I don't add it. But this would give a picture. So what I'll explain in continuation is, well, what is known, at least, in which case we can prove those things, and in which case we can either conjecturally or with theorems use special values to prove deep arithmetic results. That's mainly this part that I want to explain. But so I will study more concretely and more completely this Hasse-Weil data function that I have defined very quickly here. Okay, I think it's 6 o'clock. I should stop some. Okay, that's it.